his computer.
Okay. Just hit that file.
Oh, okay. You're way ahead of me.
Thank you.
Go ahead.
Good morning. I was here last year to talk about ARISSat, and some interesting things have happened over the last year. This is what we showed, that the various modules that we had that we were going to put in the spacesuit and take it up to the International Space Station and put it out. And then this was in May, and this is the demo of what we were going to do. We were going to have the astronauts flip the switches to enable the timers so that it wouldn't transmit for 15 minutes, so it could get far enough away from the space station. There's a camera on, 4 cameras on there. There's a transmitter receiver module. Then inside the suit is this box in the lower left and the experiment in the lower right. And then there were solar panels that were going to go around the body, which are coiled here in the front. So everything sounded good on in last May, and we had the IHU module that was the main control module for everything. There are 4 boards there. The bottom one is like a bus or a backplane, and all around the edge are the connectors for the peripheral, so we could do a lot of really interesting testing on this without having to take the stack apart. The next board up is power supply board. The board with the LEDs facing you is the IHU board, which is essentially the computer controller, and on the top is the SDX, which is a software-defined transponder board. There's the camera that we're facing 4 directions. One of them was up. There are dual 70 centimeter, 2 meter antennas on the top, and these are the switches and the LEDs to tell when different things were in safe mode. So that all went on the helmet. There's a perspective of the solar panel. These were given to us by NASA. They're SMEC solar panels from that particular project that got canceled. So like you can see, it's 19 by 10 inches, so they're fairly good sized solar panels. And when we had the entire Russian Orlan spacesuit, we had plenty of room to put those. We also were doing an experiment because we're trying to do a lot of outreach. This is from students at the Kursk State Technical University in Russia, and their particular experiment is going to sit on the was going to be on the spacesuit, and it's going to measure the difference in the vacuum as the satellite spirals into the Earth. And we were told that that hasn't been measured, so that's some new information. There's a picture of their sensor and just a regular serial port on the end to do the data communication. There's the Russian battery. This is a silver zinc battery that actually goes in the space suits to power them during their extravehicle activities, and it's, like I said, silver zinc. It's used for long duration deep discharge operations because it's in the spacesuit. Since this was given to us, it's a $40,000 battery. We're going to be using it in a completely opposite method, where we're going to do shallow discharges and charges every 90 minutes. And even silver zinc manufacturers in the United States aren't sure how this is going to perform, and neither were the Russians. So this will be an interesting experiment in itself, just to see how this battery technology adapts to this particular mission. This is from the last year. We have 2 connectors on the left that are for the solar panels. There are 3 of them that connect in each of the 2 locations. The 4 connectors on the right are for 4 different experiments, and we may increase that to 6 in the future. In the back, there's a large 50-pin cable that goes to the rest of the units, and a power connector on the back. Here's a fairly busy diagram that talks about the IHU, which is the integrated housekeeping unit, and the other things on the satellite that it talks to. And you'll see there are SPI buses, I2C buses, serial buses. So almost every bus that's available on those particular PIC32MX processors we're using to communicate to other chips and systems in the satellite. Here's the special SDX. This is total software-defined radio transponder. It has 10.7 in, 10.7 out. So this will work with any other system that if you want to do HF in and 2.4 gig out, you just have to bring everything down to a 10.7 IF, and you can change the frequency seamlessly. So it's a real nice system, and the whole point of this is that we're doing this in a modular fashion so it can be easily reused. One of the things that we've had problems with in the past is that we've developed one satellite. Well, we're doing 5 of these. 2 of them go to Russia, 1 is a working prototype, and 2 others are going to be space ready, sitting on the shelf. So we'll have things to respond to opportunities that come up quickly. Then in July of last year, because they were putting 13 astronauts in the space station at one time, they needed to do some house cleaning. And part of that was to send our Orlon suit out to burn up in the atmosphere. But we responded the very next week. We met down in Florida, and we're lucky enough to get Bob Davis to sign on and help us. And there he is taking the SMEC solar panels as the things we had to build the satellite around. So now we had solved one of the problems that we were facing. We had 6 surfaces that we could use, so we would always have some kind of solar energy, and then we could easily fit all the modules that we'd already developed in those boxes inside this structure. So we went from the earlier one to this. We just had to shuffle a few things around. We had to take the cameras out of a box and mount them on a flat surface, and we took the max power point trackers that convert the solar panel energy to different voltages. Well, the different voltages are in the power supply board, but it also charges the battery. So those are about the only 2 changes. We also took advantage of this to separate the 2 antennas, so we have a separate 70 centimeter and 2 meter antenna that we could put on the top and bottom. So that's the structure that Bob came up with. It's nice aircraft aluminum around the side, the same units, the RF unit for the transmitter and receiver. The IHU is the housekeeping box. The max power point trackers do the solar panel conversion and go into the IHU. The battery is there, the switches are on the top left, and the cameras are on the top and bottom. This is probably one of the bigger things. Before, you remember the connectors to the IHU enclosure came in from the sides. So in mounting this, we had to change the interconnect board and put the connectors on the other side, and then put all the connectors on the lid that actually sits upside down. But that made it much easier to assemble and operate and fit into here. But the circuitry inside didn't change. It was just how we interface. So being modular has really worked out well on this. So we were able to adapt quickly. And that's what it's going to look like. The little T-pins on the side is we have to have covers for the solar panels so that when they're on the International Space Station, they don't get bumped and broken and release their glass solar cells. So we have to have those on there, and then the little clips beside them are attachment clips so that the pins don't go flying out into space. So we have to tether everything to how it's, so nothing floats off. The experiment is down here in the center. The 2 meter antenna is in the top. The safety switches you see from before. And then we have 4 handles around the side that exactly match the Russian handles that are standard outside this. And so those are what we use to hold it and mount it and for them to take it out. And what they'll do is they'll go into the interlock, take the solar panel covers off. 1 astronaut will be holding by the handles. They'll take the 4 off and then go out. Well, there's also a bag that'll go around it just to help protect it a little bit. Because they didn't want the sun hitting the solar panels while they were outside very long. Although the switches cause an interlock, they didn't want the battery overcharging. So there are three levels of safety built in, which is all part of a good learning experience that the team has had, and we've brought along a new generation of people that are learning all these requirements to allow us to better develop new satellites and meet these requirements from the beginning. So this has been an interesting project because it's been developed all over the country in about 14 different locations. So we've done that by having meetings in Phoenix 5 times in the last year and a half, and we'll all come together and work for 12, 14-hour days to actually put all our pieces together in one location. We have weekly teleconferences with the software team, with the mechanical team, with the entire team. So we spend a fair amount of time on Skype and different ways. But I found that the biggest problem is people not talking to one another. So you just can't have enough of these short. We don't let any of them go over an hour, but as long as everybody is talking frequently, things get done a lot better. We've had 2 NASA safety reviews, preliminary, and we're going to have another final review, and that's been a great process. We've also done a design review of the entire satellite. We got together for 3 days in Florida again, and just sat there in the room and had 23 presentations over that weekend, going over every part of the satellite. And these presentations are available on the internet. You can go to the AMSAT.org site, click on AO51 and then design review, and you can look at all the different descriptions of each of these segments of the satellite. So I encourage you to do that. Here are the 4 space frames that are flight worthy. The one that we have in the AMSAT booth is our prototype. It has all the modules inside. We turn it on and you can hear the CW, the BPSK, the FM signals, and actually use the transponder. People out in the satellite demonstration area we've done that a few times, have actually gone through the transponder, so you can see that working too. This is something that last week I was in Florida working on the thermal vacuum chamber. Down at the bottom is a heavily insulated tank with a copper heat exchanger, and so I went down there to do testing on the modules, but spent 3 days getting all this up and going. But it was a great experience, and we have a really good thermal vacuum chamber to use in the future for other projects. The switches you can see in the front, we have Lou McFadden put together a instrument plate that passes through 119 signals. So we'll be able to check lots of different modules in the future and have wires through. Over on the right, there's an RF box that has 6 RF connectors that come through the vacuum. And the large bell jar and cover is at the top. The vertical sheet is just a large piece of aluminum that we bolt the components to, and on the back is another heat exchanger. And this cable that goes essentially through the center goes down here from the tank up through the metal plate to cool everything, and then cycles back down. And on the back, there are the modules, or some of the modules, there are all the modules. The cameras are up here on the right, but all the modules are mounted to that plate. And there's the tube we found some really nice silicon solution that goes down to minus 170, so we can get this really cool and do some good testing. On the back of the plate, this is the heat exchanger. We just have resistors to do that heating, and we're able to control that pretty well with just a power supply. So we can go heat to cold. Now, we can't do a quick heat exchange, but it's more than adequate for half an hour. So in February, we found out the Russians wanted to change the call sign, which seems like a fairly trivial event. but we'd already recorded all the ID messages. We'd put them in all the CW. It turned out to be a little more than just a trivial thing. But that's the call sign. And the big thing is that we're looking at continued operation and cooperation with the Russians on this. And the RS-0 part will stay, and then we'll update that next numeral for future missions that we do together, be them in a spacesuit or if we have hardware satellite to do. So the call signs will just follow in sequence. There are cables. Larry, are you here? Larry Brown is over in the AMSAT booth. He's just done a beautiful job doing all this cabling. You can imagine 50-pin cables times 5, and with thermistors on them, then cables between the solar panels. So he's just done a beautiful job, and you can see his cables over in the demonstration area. This is the band plan using the software-defined radio. This particular one has 40 kilohertz wide, and we're going to be doing FM signals, CW signals, BPSK signals, and that transponder simultaneously. So in that 40 kilohertz, we'll have all those different signals. In the FM, we're going to have voice ID, 6 voice telemetry values. We have 27 children's greetings in 13 different languages from around the world that will be broadcast. And then we have slow scan pictures from the 4 cameras that are on the satellite that'll be coming down as we take those. So the big part of this is to interest children around the world in science and engineering, and we have things like secret words embedded in the messages that it's just a little contest or interest. But you know, they're able to just take a simple FM radio and listen to what the temperature is on the outside of the spacecraft and on the inside, and how many volts the battery has or what the current is. And then we also have telemetry coming down in the BPSK, as well as the Russian experiment data that they collect once a day for 90 minutes, an entire orbit, to see how much the vacuum changes as it approaches. This is a picture we took last year at Dayton. The one on the left is the BPSK signal. The one in the center is a CW. You can actually see the dots and dashes in the waterfall display. The one on the right, it goes down. At the bottom is a slow scan, so you can see how stable it is as it's switching between the tones. Then there was a break, and then you can see the audio above that. So that was a nice little screen grab. The video, like I said, we have 4 cameras, and that's a good bit of information. This is a picture that was received from it transmitting. It didn't blow up very well, but gives us a good quality receiver. We have the 4 cameras, and when they were in the box, we could actually point them different directions. Here we had to mount them next to each other, so we have this nice little mirror that we built in to take a picture out the side and straight up. There's our downlink station receiving all 4 of the signals at the same time. That was here last year. We just got a new logo developed for this, and I was pleased with it. We have a number of the team members in here. Would you stand up for the ARISSat team? And I'll give Bob Swerdling's over here. He just came by the booth last year and wanted to volunteer to help, and within a month he was drawing drawings late at night trying to help to get these done. Bill Reed's been with us a couple of years, working on a lot of the software and the telemetry. Doug Qualiana is going to be doing the ground station software, and he hopes to eventually have everything in one package. You can just hook a radio to it, it'll decode the CW, it will display the slow scan television, it will show the telemetry data and the Russian experiment data. I mean, we want to make this easy so that teachers don't have to spend they're not going to spend 4 weeks learning how to do this. It's just a simple software package. They can put data in, and there's it out. In addition, we're going to have a worldwide internet connection so people can send data in from all around the world and have access to it. So you can actually watch collections of telemetry that's going on real time, and then we have it stored in the database. And Barry, of course, is the president who's helping us get all this done. So that's the future. We're planning on sending this to Russia the 1st of July. It's going to go up in a Progress vehicle and stay on the International Space Station till about December, when they have an EVA plan to take it out and just manually push it away from the ISS, and we expect it to orbit 6 to 12 months. And depending on the battery, it will go for as long as it can, and then it will burn up in the atmosphere like things normally do. Any questions? Quick question? We have time? Okay. All right, thank you.
Let me just make a comment about the ARISSat process that perhaps you may not be aware of. We signed a couple of weeks ago a protocol with RSC Energia and NASA defining the roles and responsibilities of the various organizations that are involved with ARISSat. And I just want to point out a couple of things. One is working with NASA. Originally, when this was started, this was a Russian-ARIS relationship. NASA really didn't show a lot of interest, in my opinion. They have come to the plate and have helped us in a number of ways. One is that the NASA safety review that Gould made reference to, they are doing the safety review on behalf of both RSC Energia, which will also be involved, and AMSAT. It's because we are going to the space station where there are humans living. So we have to meet their safety standards to place our equipment on board the International Space Station. RSC Energia is doing the upmass to the space station, and they're training their cosmonauts to do the release during an EVA. So the launch, if you will, the cost of the launch is being borne by RSC Energia. And the underlying basis for this relationship is the fact that this is an educational satellite. The Russians are anxious to see educational payloads released from the International Space Station, and that's our ticket to ride, so to speak. As NASA's become more aware of what we're doing, they are beginning to express some interest in a ARISSat-like project. So while it's difficult to predict what they may be willing to support in the future, a successful deployment of ARISSat does, in my opinion, open the door for NASA support of similar opportunities. So it's quite conceivable that you may see the traditional SUITSat in one case and the ARISSat in another. The transition from SUITSat to ARISSat is really a blessing as well as a challenge, because having a structure now means that we can have these things stored, ready to go. Basically, insert the battery, turn it on, and you're ready to fly. Rather than have the SUITSat where the cosmonaut has to put the equipment inside the spacesuit that's already on board the ISS. So from a quality control perspective, this does help us in terms of coming up with a better, what I call, a product. The other thing I wanted to mention too is that, again, in terms of relationships, credibility for AMSAT is extremely important, not only for our members, but for the folks that we're trying to solicit donations from. So ARISSat's critical to our future, not only in terms of the concept of what we want to do, but executing upon it. So the next few weeks, between now and July 1, when we have to deliver, is extremely important. We are going to be doing some vibration testing. We're working on final arrangements with Wallops Island, where that testing will take place. So you saw pictures of the thermal vac chamber. It's in Orlando. We do that, but we also have to do vibration testing to meet the qualification standards of RSC Energia to have our equipment placed on board their Progress cargo vessel. So a lot of work's to be done between now and July 1. NASA is helping us with our export licensing. I mentioned ITAR earlier. We are covered under the NASA RSC Energia relationship, so all of our conversations that involve the Russians, NASA is involved with. We are protected, if you will, by the agreements that exist between NASA and RSC Energia, and they're helping us with our export licensing to allow us to have this thing shipped out of the country to Russia. So that protocol has been extremely important for us in terms of pulling these pieces together to allow this thing to be actually exported to Russia for upload to the ISS.